One second. Yeah, check out. Here there is one step which is which is OH minus. When you treat that with OH minus and heat is being facilitated, then first you'll get an uh, thalimide. Thalimide will go like this: double bond O with N with minus. Okay, and this minus is the one which will which will attack on here, remove out this Cl minus. So on removing out that Cl minus, we will get the compound like this. We will get N double bond O with CH2 COOET. And this on hydrolysis on and heating, we will get, this is hydrolysis and heating. It will convert into an acid group here, and then it will convert into acid group here with NH2, and the other part will be ethanol. This is what you will get. So basically what you are getting is amino acid. So this was the preparation of amino acid as well. Clear, beta? So this is an important sequence of making amino acid. So please do check. The same application is there in F also. F is the same thing. Here, first with OH minus, you will create that thalamide ion like this minus, and that when you're reacting with phenyl bromide. Okay. Now, problem here is phenyl bromide does not make any reaction as such. Got it? So here the reaction will stop. So nothing would happen. Because here I require to make an SN2 type of mechanism, and on the phenyl position, SN2 is not going to happen. Correct? So it will only stop at this point. Is this part clear? Right. See the next one. NH2 here. Again, NH2 can attack on this particular nitrogen here. So what do we get? So we will get this as O minus and NH3 plus. And this O minus can take H plus from here, converting that into OH and NH2. So this is the product you will get. Similarly, N3 minus, you will get this as O minus N3. And just now we learned that N3, this will convert into OH on hydrolysis. N3 will convert into NH2 plus N2. So that is the product. Okay. Right. Next. Al2O3 and heat here. Ammonia can act like a basic group, right? First, OH, OH will react with Al2O3 here. So something like this, you can see, makes this as a good leaving group. And that's when ammonia as a base will extract proton from here, relieve this group on heating, converting that into a double bond, and that H2O will be coming out and Al2O3 will be separated out, right? So this is a basic elimination reaction here. Okay. So quickly check out E to H. Any doubts? Clear? Diya, any doubt? Right. Next one. Ammonia is a good nucleophile, so it can make an ARSN2 reaction, and that can replace the fluorine and get NH2, NO2 plus HF. Now, the next one, when you have NaNH2 and ammonia, this is a benzene mechanism. Let me remind you how the benzene mechanism works. Cl, H, and this one. This is chlorobenzene. NH2 minus will actually take away H plus from here, pushing this pushing this lone pair electrons, removing the chlorine. That's how we will get a benzyne. So this is a benzyne form. On the benzyne form, NH2 again acts like a nucleophile, attacks it, and thus giving us NH2 with minus charge. And that will take H plus from liquid ammonia, thus giving us aniline. So you can see the product what you will get is aniline. The mechanism is via benzyne form. So this is the mechanism that you will notice. Got it? Okay. Next, we have protonation being done, then cyanide is being added here. So we can see that first we will get OH2 plus, clear. This will relieve into formation of carbocation. That carbocation can be attacked by cyanide here, getting it as this cyanide form. And this cyanide form, when you treat with OH minus and heat, basically you are making an hydrolysis. So that will make this as CO minus Na plus. This is the product you will get. Got it? Please check I and J. Right. Next. This is a basic reaction which we have learned it, that NH3 will add on to this double bond. So we'll get this as a double bond NH. Okay. Basically, this is helping it to remove out that hydrogen, which is extra hydrogen, which is present there. That's it. Okay. Same way here, we can get double bond NCH3. And here, if you have a secondary amine, imagine when you have a secondary amine, you always write it in the enol form first, and then notice this, we have methyl and methyl here, and then remove out this water molecule. Got it? So on removing out that water molecule, what do we have? We'll get double bond here with N, methyl and methyl. This is the way it will appear. Correct? So this is the product you will have. Got it? And this one, COOH or HCONH2. Got it? Amides on heating. Okay. So when you have HC double bond O NH2, this on heating will again give you carbon monoxide and NH3. So again the reaction type is the same. So it will give you NH3. So that NH3 will again convert into imine form. So this is the product you will get. Clear? Next. This is Hoffman bromamide degradation, HBD reaction. In Hoffman bromamide degradation, first you will get C double bond O, N, NH attached with Br, and in the presence of OBr minus, again this H plus will be relieved out, and you will get this as double bond O and Br with minus. This phenyl will shift, this group will go, Br will come out, so we'll get phenyl and double bond C double bond O. So this is isocyanate. And isocyanate, usually it is always mentioned with hydrolysis. Okay. Even if you have NaOBr, you assume that there is under hydrolysis, and you'll get this as amines and Na2CO3. So this is the product you will get. So final product is 1-degree amine. So basically, whenever you have an amide, simply remove out this C double bond O, that is HBD reaction. Okay. So here also it is like an amide group only. So we will have this as with a secondary position here, right? So we'll have this as NH double bond O. First the bond, when you try to react with Br here, right, lone pair will attack on this Br here, okay, and then the bond will break onto this side. So we will get minus here, sorry, let me write one of them, minus here and Br here, and the other side will have a double bond of plus, on which OH minus will be attached, and thus we will get this as double bond O N Br, and here we will have double bond O OH, correct. Now Wolf rearrangement will take place from here, Br will go away, lone pair will come here. Now notice how many carbons we have: one, two, three, four carbons, correct? Four carbons we have, and the last carbon we have acid. So we will have this as CH2, 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 and the last carbon. Now this will be CH2 connected with N, double bond C, double bond O. Now that on hydrolysis will give you HOOC, CH2, 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 and NH2. This is the product that you will get. Please check these two reactions quickly. The next one is also Hoffman bromamide degradation. In this case, you will notice again we will have this as double bond O NH2. Now listen up. First thing is that NOBr is a basic solution. That means it will have OH minus. That OH minus will replace the bromine here first. And this is what you will get. And then you perform Hoffman bromamide degradation. So you will get this carbon having OH and NH2. Both will be present. Agreed? And since it is in a basic medium, it will get this as O minus and NH2. And this O minus will push to remove this NH2. And what you'll end up getting is an aldehyde. Okay, so instead of amines, you will end up getting aldehyde. Got it? This is the limitations of Hoffman. We have learned it as limitations of Hoffman reaction. Another thing is that when you have such bulky group here, correct? See, 1, 2, 3, 4, 5, 6, 7, 8. This much amount of bulky group if you have. So CH3, CH2, 7 times connected with C double bond O. Let me check again. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 times. Then we have C double bond O NH2. So here we will have N minus Br, isn't it? But problem is here the rearrangement does not take place, because such bulky group will not be able to undergo rearrangement. So this is where you will stop the reaction. Okay. So no product formation after that. This is the same thing I just told you. So if you already have an OH group and here you will get an NH2, correct, by Hoffman bromamide degradation. So you will have this as O minus and NH2 in the basic solution. This will push to remove NH2 and thus giving it as a keto form. This is what you will get. In the triple bond also, you will have like this, we have a triple bond here connected with NH2 here, correct? We have NH2. But in basic medium, when you have it in basic medium, what would happen? This NH2, the lone pair will keep on pushing here till it becomes minus. So, uh, what do we get here is that this NH2 minus, you know, 1 second, Mm, double bond O, NH2 is formed here. Correct. The lone pair will push here, so minus charge would come here, correct? So that will take H plus from the solution. So after a while, what you will notice is that this will convert into a cyanide form. So 1, 2, how many? We have 1, 2, 3 carbons, right? So that will become a cyanide. So we will have this as CH3, C, CH2, C triple bond N. So instead of amines, now you will end up getting cyanides. Clear? These were already given as limitations of Hoffman bromomide degradation in carboxylic acid notes. Okay. Next, notice here, when you conduct of Hoffman elimination, there is no cross products that will come across. So that means you will only get pH NH2 with a star here, and you will only get this one NH2. So there is no crossover products. So remember, no crossover products. Right. Next, again here also Hoffman bromomide degradation. What would happen is the configuration will retain. So nothing will happen here. So NH2 will be the same and Na2CO3 will be formed. So whatever the configuration is, original configuration will retain. That's another important point of Hoffman bromomide degradation. Okay. Next, we have pH double bond O NH. This will become OTS. This is Lawson's reaction. So again with OH minus, you will be removing out this H plus. So you'll get this as pH double bond O N minus OTS. OTS is a good leaving group. Wolff rearrangement will take place. OTS will leave. Again, you will get this as N C double bond O, this one, isocyanate, which on hydrolysis will give you amines. So this is the product. So this is same as Hoffman's reaction. We call it as Lawson's reaction. Got it? Next, cyanide reaction. So cyanide will undergo reduction here NH2 with NaBH4 no reaction. Okay, with sodium and ethanol here, correct? So this will again undergo reduction. So we'll get this as CH2 NH2. H2 by nickel will also make reduction CH2 NH2. Correct. So these are the products you will get. Next, isocyanate will give you the same thing. So you will get this as NH2, sorry, NHCH3, and with NaOH, this will become NH2 plus HCO minus Na plus. Got it? Because it will undergo more like hydrolysis and open up. Please do check any doubt in these reactions. Finished?
Yes, sir.
Right. NO2. NO2 can be reduced into NH2 very easily. Whatever the reagents, what are all the reagents we can use? Check out. First, we can use H2 by nickel. We can use lithium aluminum hydride. We can use zinc in HCl, tin in HCl, or iron in HCl. These are all the reagents that can be used. Okay. But when it comes to benzene group, then lithium aluminum hydride doesn't work. Okay. Rest of them will work. So the same reagents except for lithium aluminum hydride. Okay. Because lithium aluminum hydride this time will give you diazo group. Got it? Next. Next reagent, if you notice, selective reduction. That means only one NO2 should be reduced. For one NO2 to be reduced, we can use it as Na2S. We can use Na2SX, that means any form of it, or NaHX, HS. Got it? So all of these salt forms, sodium sulfite salts, followed by hydrolysis, that will give you selective reduction. Okay. Same thing here. This can be taken in terms of ammonia also. That is ammonium sulfide, ammonium bisulfite, like this. In any case, they all will give you same reaction. Okay, this will give you same reaction. So what are we going to do here? And if you already have a reduced form here and NO2 is present here, the opposite side will get reduced here. This side will get reduced. Okay, and if you do have three groups here, correct, then can notice that, sorry, methyl is there. This NO2 is not connected anywhere. Okay, here methyl is there. If you have methyl here, correct, then the one which is closest will get reduced. So NO2 and NH2 here and CH3 here. This will get reduced like this. Okay, these are the product that can be formed. Next, SnCl2 will make a complete reduction. So that means you can have NH2 formation here, NH2 formation here, and methyl here. Done? Right. So this is a separate question here. Okay. Please go through this reduction quickly. Sorry, I made it opposite beta. The uh, groups which has NO2 on the side, that will reduce on the opposite side. My mistake. This one I made it wrong. It should have been NO2 here. If the donating is there here, so it will come at this position. This is donating, right? That's why it should go there. Hmm. Finished. And if you take one equivalent, see, same question, I'm taking it as one equivalent. Okay, so that means I'm not taking SnCl2 in excess. If you take one equivalent, the reduction in that case will happen on the side ones. Okay, uh, here NH2 and this NO2 will remain. So basically here question was supposed to be comparative of these two. Okay, when you take this one with methyl group present, then the opposite side will get reduced. When you take it with SnCl2, the ortho side will get reduced. Okay, next. Next, check out with nitro. First one, we know that here we will get simple amines here. Now, when it comes to lithium, I told you that in the case of lithium, now the reduction is different. In this case, azo form will come, that is N, double bond N and pH. This is the product that you will get. Got it? And if you have zinc with neutral medium, in that case, hydroxylamine will come, that is NH and OH. Zinc in basic medium. Suppose if you have zinc in basic medium, like so NaOH or methanol, then it will be same as lithium aluminum hydride. Okay, and zinc only with NaOH, correct? If you have zinc only with NaOH or glucose, you can take or glucose, anything. In that case, this part will also get reduced, NH and pH. Got it? This is called hydrazobenzene. Okay, this is called only azobenzene. Okay, this is uh, hydroxyl amine. Okay, which amine? Benzanamine. Hydroxyl benzanamine. Got it. Clear?
Yes.
Next, if you have arsenic, suppose in case if you have an arsenic, then same azo will come here, correct? This one will be same azo group, except that nitrogen will also have a oxygen bond. So how do we call it? It is azoxy. Azo will become azoxy. There is one oxygen present. So this is called azoxybenzene, right? So these are the parts that you will be asked. As much as JEE mains is concerned, one, two, uh, three. These three could be asked. Got it? So do check in what case what you will get. Clear? Next. We are reacting with this HCl. So in the presence of HCl, what do I get? MENH3Cl plus and minus here, right? So simple amines, when you react with HCl, this is what you will get. All right. The first cases are clear, beta. I hope there is no doubt there. Yeah. Right. Next, the minute you start heating it, right, that means it will start favoring the Cl minus to start moving around. So basically, it will have now CH3, NH3 plus, and Cl minus is open. So Cl minus as a nucleophile will attack. Remove this one, and you'll get CH3Cl plus NH3. Got it? Same logic here also. Dimethyl NH2 plus and Cl minus. The minute the heat is given, now you will get this as methyl, methyl with chlorine and NH3. Okay, got it? Sorry, not NH3, RNH2. Two methyls will not be there. No? Let me rewrite that. With the structures, I'll write methyl, methyl, uh, carbon connected to NH2, sorry, NH is in a secondary position like this. NH methyl, methyl, and I got one more hydrogen, so plus and Cl minus. Okay, now the same Cl minus will attack the minute you start heating it. So this time the Cl minus will attack here, the bond will break here. So what do I get? MENH2 plus MECl. Got it? In tertiary also it is the same case. You will have Me thrice NH plus and Cl minus. And in this case we'll have Me, 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 and we have hydrogen plus and Cl minus. So Cl minus will attack, bond will break. So MECl plus NH Me twice. So secondary amine will you will get. So here 1 degree amine. Got it? So I guess these reactions are clear. Done. Next. If you have FeCl3, then what will be the reaction in this case? Okay. See, FeCl3 basically converts into Fe. It is in aqueous form, so it will give a reddish, brown precipitate, brown PPT, and the ammonia will take away that hydrogen part of it. So we'll get this as Me NH3 plus and Cl minus. Okay, clear? In the case of silver, you'll only get complex. So silver NH Me twice plus and Cl minus, a complex formation. Soluble complex. This is a soluble complex form. Okay. Is this part is clear? Okay. Next. Br2 in a basic medium here. Okay. Just a minute. Yeah. When you have Br2 in the presence of Na2CO3, Na2CO3 is a basic medium here, like this. Okay. And Br2 in the presence of basic medium, you will have, bromine present on it. So we will get this as N-bromo, sorry, like this. You can get this as N-bromo here, like NH Br form here. Got it? Bromo form will form. Understood? And yeah, that's it. Same logic here also. We can have secondary amine here, Et and Et with Br form, and here we can have pH, CH2, NH, Br form. Next, this is carbyl amine test. Carbyl amine test is primary amines will convert into N triple bond C plus and minus. This is isocyanide. Isocyanide is a foul smelling vapor. So this is a confirmation. This is a confirmation for presence of 1 degree, known as carbyl amine test. Is known as carbyl amine test. Okay. Now this is Hinsberg test. In Hinsberg test, what would happen? First, we will get this as methyl NH. Okay. This will become TS. Got it? And then we'll have Me N minus and uh, uh, TSCl will be there. Correct. That is what it will happen. So we'll get this as TS. You know what is TS beta? This one. In case if you are not aware of the structure, this is the one. Double bond O Cl with methyl. This is tosyl chloride. So I'm not writing the entire structure, but you should know that this is what it is. So we will have like this. So TS here connected. And with HCl again the product will come back. MENH2. Got it? This is a soluble form. Okay. Next, secondary amines N here. Now this is a white PPT. This is white PPT. Here TS. This is also white PPT. But on NaOH no reaction. So further there is no reaction as such. With this one trimethyl amine with plus, and we will have this as TS. TS getting connected. Sorry. TS getting connected here and getting a plus charge and Cl minus. So no further reaction will take place. And it is soluble form. So this is not a precipitate. So in Hinsberg test, 1 degree will give you a precipitate which gets soluble in NaOH. 2 degree will give a white PPT which is insoluble in NaOH. 3 degree always remains soluble form. Got it? Clear beta? Next. If we have uh, if you notice the next test here, so this test is called what do you call it here? Hoffman mustard oil test. Sorry, mustard oil test. So mustard oil test is if you have methyl with nitrogen here, so NH connected to C double bond S and SH. This is what you have. In HgCl2, again you will get a isocyanate type of form. So that is methyl here, methyl with N double bond C double bond S. Okay, so basically this SH and H will go away and you will get this part, and that H2S which has left will convert into a HGS, a black color PPT plus HCl. Now this will be smell of mustard, smell of mustard oil. Got it? In the case of 2 degree, you will get this as R, I mean CH3, CH3 here, CH3, CH3 here, nitrogen is present here. That nitrogen is connected to C double bond S and SH. Okay. But further no reaction will take place because there is no hydrogen present on nitrogen to relieve that. In the tertiary, there is no reaction only. So this is mustard oil test. Got it? Clear? Next one. If you have a primary amine, this is called a Hoffman test. This is Hoffman test. In Hoffman test, basically you'll get an amide forms here. CO. This is the structure like this, right? C double bond O, C double bond O. This is OET and OET. So this, when you react with 2 moles of MENH2, it will convert into C double bond O, NH with methyl, C double bond O, NH with methyl. So 2 moles will give this product. Now this is a solid precipitate. Got it? Next, if you have, uh, you know, 2 degree, 2 degree becomes bulkier, so only one molecule can come here. So this will exist liquid. Got it? 3 degree, no reaction. So this is Hoffman test. Clear, beta? Next, this is with nitrous acid. With nitrous acid, primary amine will give you disonium salt. Disonium salt are highly unstable. It will convert into carbocation plus N2, and because it is in an aqueous solution, it will major product will be alcohol. Okay, this is the product you will get. Next, secondary amine will give you methyl N, methyl, and N double bond O will be formed. This is going to form N double bond O. Now this N double bond O suggests that this is an oily yellow liquid, correct? The formation is called the conformation for second degree amine, also known as Lieberman nitroso test. This is called Lieberman nitroso test. Lieberman nitroso test is specifically for second degree, 2 degree amine. 3 degree does not make any reaction. Done. Next, this is diazonium salt. Diazonium salt will be stable as long as temperature is below 5 degrees. So this is where you'll end. You'll stop it here only. All right. Secondary amine, just now we learned it is yellow oily pigmentation. So N double bond O. Okay. So this will be methyl like this. So this is oily yellow color. So Lieberman nitroso test LNT. Hmm. Next, when it comes to tertiary, now this time nitrogen will not take that NO group. It will make an electrophilic aromatic substitution. So this is a major product you will get. Very important reaction. The I1 is very important. Please remember how it works on aniline. Okay. Clear? Next, reaction with KMnO4. See, wherever NH2 is there, you imagine just like alcohol. And when you have alcohol, what you used to do with KMnO4, you used to oxidize them and convert into acids. So do the same thing here also. You will get this as an acid. Okay. And same way here also, if you have 2 degree, you will convert that into ketones. Do the same thing here also. Ketones. Okay. If you have 3 degree, you will not have any reaction. Same logic here also. But because there is NH2, that will get oxidized here and that will convert into nitro. This is important. Okay. Because while in alcohol there is no reaction, here it will go up to nitro formation. NH2 will convert into nitro. Got it? Now, if you have second degree, right? If you have 2 degree amines, so far whatever we did is 1 degree. In 2 degree amines, the coupling will happen. So that means N here and next molecules N will get coupled. So hydrazine type of a form is observed. Okay. If it is 3 degree, then oxide will form. That means O minus like this, plus and minus. This is called amine oxide. It will oxidize to amine oxide. Okay, these are the oxidation reactions. Clear? Next, if it is peroxy acid like H2SO5, in the case of peroxy acid, it will convert into nitroso group, N double bond O. Okay, so it will convert into N double bond O. Got it? Uh, If it is in a secondary amine form, sorry, this is all primary amine form only. So you'll get this as N double bond O, and here also you'll get this as N double bond O. Okay. I think this is, sorry. For primary, it will go up to hydroxylamine. So which I have to write it like this, where you will have this as nitrogen, where nitrogen is present. There we will get a double bond N and OH. So we'll get this as oxime. So if you do not have any substitutions here, it will go up to oxime form. And if you have, you know, second amine, 1 degree amine, but at a second degree carbon, right? So that will also form ketoamines here. So this is aldoxamine. Now we will have ketoxime. This is oxime as well. Only in tertiary position you'll get up, because there is no hydrogen, it will go up to nitroso. So at nitroso it will stop. Okay. And if you have it at 2 degree, then in that case we will get hydroxylamine, that is OH here. And if it is 3 degree, just as above, only amine oxide will form. So it will oxide up to amine oxide. Clear?
So could you just show the previous page 1 second?
Yeah, please check. So this will convert into nitroso. If you have peroxy acids, it will convert into nitroso. With KMNO4, it will become benzoquinone. Okay, next. In case if you have aniline, right, what are all the reactions that you will notice? Okay, so if you have uh, only aniline, correct, reacting that with mm, potassium, okay, potassium will take away H plus from here, converts into NH minus K plus half of H2, just like sodium reaction. Bromine CS2, it will make substitution at all the positions like this. White PPT. It's a white PPT. Whether it is water or CS2, you'll get the same product in the case of aniline. Okay. With concentrated H2SO4, first it will form salt like this, acid base reaction. So NH3 plus and HSO4 minus. And if the heat is given, it is not given, but usually heat will be given always. If the heat is given, then sulfonalic acid will form. So that is NH3 plus and SO3 minus. This is major. The minor would be at meta position, at ortho position also, NH3 plus and SO3 minus. Okay, this is called sulfonalic acid. Okay. In the case of concentrated H2SO, concentrated HNO3, nitration will take place. So we will get NH2 with ortho, NH2 with meta, and NH2 with para also. So all three will come here. Okay. The percentage would be different. Here this will be 2%, this will be 47%, and this will be 51%. Clear? So these are the product formations. Done. Next, AC2O, first it will form, see, first it will form NH C double bond O CH3. Acetylation will take place. Now, because the ring is not very strongly activating, nitration will happen, but only at para position. Now, this time nitration will happen only at para position. Thereafter, when you react with NaOH and heat, it will get back to formation of NH2 and NO2. So this is the product. This reaction is very, very important one. The last one is asked many times, combining with other reactions. Okay. Done. Aniline reactions are clear, beta. Next. Disonium salt. Disonium salt with warm water will directly give you phenol with N2. CuX, it is called Sandmeyer reaction. So you will get this as X substituted benzene. This is called Sandmeyer reaction. Ki, just on shaking with the solution, you will get IDO. Okay. NaBF4, now this is important. First, it will form N2 plus BF4 minus salt. If the heat is not given, then you cannot proceed. You have to stop there only. Okay. Only when the heat is given, you will get fluorobenzene, N2 and BF3. Okay. PF5HF, it is the same reaction again. Heat is given. So you will get fluoro here and we'll get this as PF5 plus uh, F6 and N2. N2 plus HF. Okay. Clear, beta? Sorry, not HF, HCl. And next, this one is also the same thing. Here we will get this as fluorine plus AsF5, AsF5 plus N2. Done. These are all fluorinating reagents. Okay. This reaction name is Boltzmann reaction. Clear? Next. The other disonium salt reactions you can see. If you have H3PO2, it will convert into benzene plus H3PO3. Got it? It will convert into benzene form. Okay. And next, if you have ethanol, with ethanol also you will get the same product. This is major product, clear? But there will be some amount of minor product where you will have OET, just like hydrolysis, alcoholysis will also happen. This is minor product, but major product will be this. And since benzene is forming, you will have aldehyde, acetaldehyde forming. With methanol, it is reverse. With methanol, benzene is minor and uh, methoxybenzene is major. This one. Okay, this is major. Na2 and Cu. If you have copper and NaNO2 here, so same thing. Basically, we'll get X here. Okay, I mean NO2 here. In case if you have NO2, you'll get NO2 here, and copper will get reduced. This is known as Gattermann reaction. Gattermann reaction. Okay, so same logic here also. HX is there means you can get X here, and X could be chlorine or bromine. This is also Gattermann reaction. Next, phenol. With phenol, you will get azo compound. So we'll get N double bond N this way. With this is phenol with OH. So this is, what do we have is a azo compound here. Got it? If you're doing it with mm, phenol, correct? Then we call it as azobenzene parahydroxy azobenzene. Okay. So parahydroxy azobenzene, what is the color we'll have? Okay. It will be usually yellow. All right. Remember this one, BPA Roy. Clear? Understood? Sorry, orange. My mistake. Orange color. Okay. If you have it with aniline, then it is yellow. So you'll have NH2 with N double bond N. This is the para amino azobenzene. Para amino azobenzene. So this is yellow. Got it? Next, if NH2 is present with two positions here, then one side you will get aniline form, I mean disonium salt form, and that will convert into like this double bond N, and the other nitrogen will connect like this. Okay, this way. Got it? Next, if you have hydrazo, you know that this is called hydrazo. Hydrazo in the presence of H plus, basically the bond between these two will break and connect from the other end. So we will get these two getting connected like this. Benzene getting connected here, and NH2 will come on the other side. Don't get into the mechanism, just remember it this way. Okay, clear? So two aniline groups connected, this is called benzidine. So we'll get benzidine form. Done. So mainly we covered almost, to the advanced level, whatever the questions that could be asked from aniline directly as a reaction, how that is being asked here. Clear, beta? Right. Now, notice this basic conversions also. Benzene to meta-nitrobenzene. Meta-nitrophenol, sorry. Correct. So, basically, we need to get this as benzene towards meta-nitrophenol. This is the part we need to get. Okay. So, start from here. Think how we can generate NO2. Got it? See, what we can do. First, you do nitration, that is concentrated HNO3. Sorry. You can get this as you can get this as NO2 here. In NO2, again you do nitration, but this time with dilute HNO3. So that would give us NO2 with meta position. This will happen at meta position. And once you get this, you do selective reduction. Understood? Selective reduction can be done by ammonium hydrogen sulfide or ammonium sulfide. Only one NO2 will get reduced. So we will get this as NH2 and NO2. Then you do diazonium reaction, that is HNO2. Okay, let me put it here with HNO2. If you react that with HNO2, what do I get? I'll get diazonium salt. So I'll get this as N2 plus Cl minus, and NO2 will be present. And diazonium salt, when you react with warm water, so what do I get? Phenolic group. Done. Very important. Okay, learn it, write it down. How to convert benzene towards M-nitrophenol. Check. Finished. See the next one. Second one. We have benzene to 1,3-dibromobenzene. Benzene to 1,3-dibromobenzene. 1 and 3-dibromobenzene. Agreed? Here. Correct. Somehow again we need to get this form. Clear? Can you check out? We can do the same thing again. You know? We could do the same thing again. So we can have concentrated HNO3 converting that into NO2 here, and again make dilute HNO3 reaction, so that you can get nitro substitution again here, and that this time instead of selective reduction, go for complete reduction. You can take SnHCl, so we will get two aniline groups here, NH2 and NH2, and then make a diazonium salt formation, so that is constant, sorry, HNO2. So you take excess amount of HNO2, so you'll get diazonium salt on both sides, N2 plus and N2 plus. And now you do Sandmeyer's reaction, that is CuBr and heat. That's it. Got there. Please check. Is the reaction set clear, beta? Next, aniline to 2-bromoaniline. Okay, aniline to 2-bromoaniline. You have aniline here to 2-bromoaniline. NH2 and bromine should be here only. Okay. So we should get only one bromine. We should not get multiple bromines in this case. Alright. Then how do we need to do this part here? So first of all, you need to somehow manage to hmm, one second. Here I need, let me start the recording. Right. Sorry, let me show this one by one. First with acetylation, this is the part. Then dilute HNO3, nitro will come at para position. With bromine, because the para is closed, now only one Br will come at this position. Then reduction with SnHCl will make a NO2 reduction. Then HNO2 will make a diazonium salt formation. And now I am using H3PO2. So by which it will convert into hydrogen form. So C double bond of CH3 Br at the para position will get hydrogen. And now you use NaOH and heat. So you will get back to that original NH2. So NH2 Br plus CH3 CO minus Na plus. Done. So that's how you get the product. Clear? So please check out, very important journey. This one also, make a note of it. Clear, beta? This is one of the suggestions. You first react with HCl, you know, then you will get this as NH3 plus Cl minus, barabar. Now you do nitration, concentrated HNO3. So what happens here? In this case, you will get a para compound because NH3 plus is a withdrawing group now. Because it is withdrawing group, now you'll get NO2 at para position. Agreed now? Sorry. Clear? And now you again react with NaOH, right? So you will get back that NH2 back here with NO2. Done. Now you do HNO2. So with HNO2, now the nitration will take place. I mean the diazotization will take place. Sorry, first reduction. I forgot to do reduction. We'll have to do SnHCl. So we have to make a reduction here. So we'll have to make NH2 and NH2. Done. Now once you get this, it is easier because now you just have to react with HNO2. And as you react with HNO2, what do I get, beta? As you react with HNO2, you'll get this as N2 plus and N2 plus. And these two can be done by warm water to get this product. Done. Finish. Clear, beta?
So could you show the second one?
Second one. Please check. Reaction here. Okay. See. The last reaction is this one. So if you have benzene, you try to react this with first HNO3 in the presence of concentrated H2SO4, you will get a product A. Got it? Then uh, react that with Fe and HCl, you will get product B. That you react with Br2 and H2O, you will get product C. That you react with NaNO2, okay, in HCl, you will get product D. That you react with H3PO2, you will get product uh, DE. Got it? These are the products you can get. Clear? Sorry, last here. Uh, E, when you react with concentrated HNO2, HNO3, EF, you'll get product F. Got it? And F, when you react with tin and HCl, you will get product G. G, when you react with product CuCN, you will get He. Correct? E, when you react with, when you do hydrolysis, you will get E, G, H. Sorry, this is H. HI. Okay, clear? This, when you react with ammonia and heat, you will get J. Correct? J, when you react with Br2 and NaOH, Br2 and NaOH, you will get K. Got it? Understood? And K, when you react with K, when you react with um, CHCl3, KOH, you will get L. Okay? L, when you react with lithium aluminum hydride, you will get M. Okay? M, when you react with HNO2, you will get N. Got it? And you need to find out number of nitrogen atoms in compound N. Uh, this is the sequence. This will give you the complete gist of amines now. Okay, so try that out.